Now in this chapter we will be discussing about the nature of light. The study of light has always fascinated scientists from the ancient time itself. Initially it was thought that light is a wave, then some people started thinking that light is a particle, then again a few people started thinking that light is a wave, then again it was debated whether light is a particle or a wave, and then finally it was settled that light behaves like both a wave and a particle. So in this particular chapter we will be discussing about the wave property, wave nature of light. So the chapter is light waves. So as discussed, what are waves? Waves are something that transfer energy without the actual transfer of any material or any particle. So waves are something which can transfer the energy from one point to another point without any actual transfer of any material or particle. Now the light waves show various phenomena, various properties like reflection, refraction, scattering, dispersion, interference, diffraction, polarization, and one more property is there, which is the photoelectric effect. But this photoelectric effect is shown by the particle nature or particle property of light. So these are the main properties that are shown by the wave nature of light. So in this particular chapter we will be discussing about interference, diffraction and polarization. These three topics will be discussed in this chapter. So let us first discuss a few basic things and then about the wave property of light, and then we will start with these three properties. So the formal study of light started with Newton. It is not that nobody before Newton studied light, but the major breakthroughs or major study were done during the time of Newton. So first of all, according to Newton, he considered light as a corpuscle. Now corpuscle means particle or discrete chunks. So according to Newton, light was a particle. But then there was this scientist called Huygen. Christian Huygen suggested that no, light is not a particle. Remember, corpuscle means particle. So according to Huygen, light was a wave, not a particle. And this Huygens wave theory was confirmed or was given more proof by the experiment done by Thomas Young, which is also called the Young's double slit experiment. So by which it was very much proven that light is a wave. But then again a few things happened which again made the wave property of light stronger, and Maxwell also suggested that light is a wave. But after that Albert Einstein came in 1905 and he explained the photoelectric effect using the particle nature of light. So according to him light is a particle. So again the debate started that whether light is a wave or a particle. So then finally after the advent of quantum mechanics, it was suggested that light is both a wave and a particle. So it was called the wave particle duality. So according to quantum mechanics, according to our present theory, light behaves like wave as well as like particle, which is called the wave particle duality. So we will first start with the Huygens wave theory in this particular chapter, and then we'll understand about the experiment done by Young. So Huygens wave theory. So what is Huygens wave theory? So it is quite simple. He assumed that first light travels in the form of waves. Okay, this was his first postulate. Secondly, he suggested that these waves travel in all direction with velocity 3 into 10 to the power 8 meter per second. Then thirdly, he postulated that the whole universe with all matter and space is filled with luminiferous medium called ether. Matter and space is filled with a luminiferous medium, which is called ether, with very low density and high elasticity. We will understand why he postulated all these things. Then he postulated that the sensation of different colors is because of the different wavelengths. Sensation of different colors is due to different wavelengths of light. Then he suggested that light waves are transverse in nature in order to explain the phenomena of polarization. Again, we will understand about all these things in this chapter. The polarization is not shown by the longitudinal waves. So initially he suggested that light is longitudinal, but he could not explain polarization. So he suggested that instead light is a transverse wave. So these are the few postulates that he had. That in this all these postulates just focus on one important postulate, is that the light travels in the form of waves. Now Huygen explained how the wave traveled using a property called wavefront. So he introduced a new term which he called a wavefront. So what is a wavefront? So according to the wave theory of light, a source of light sends disturbances in all directions. So what is a wavefront? Wavefront of a wave at any point or any instant is the locus of all the particles, in any medium which are being disturbed at the same time. And are in same phase. same phase of vibration. So for example, let's say we have a point source. So this point source will give off light in all the directions. Okay, so how will the wavefronts of this point source look? They will look like a circle. If you talk about 2D, it will look like a circle. If you talk about 3D, it will look like a sphere. So we all usually always talk about 3D, so it will be a sphere. Okay, imagine it to be a spherical shape. So what does the meaning of wavefront is here? So focus on all these points. So all these points are in the same phase. Okay, all these points are in the same phase. What does this mean is that all points at this location are, let's say, in this phase, that is they are high, or all points here are in this particular location. So all the particles in this circle are in same phase. All the particles in this circle, they are in same phase. So what is a wavefront? Wavefront is the locus of all the points which are in same phase with one another. So there are different kinds of or shapes of wavefronts. So one is for the point source, which is spherical. Now another type of wavefront can be a cylindrical wavefront. So let's say we have a source which is in the form of a line. Okay, linear wavefront. So let's say we have a linear wavefront. So for this linear wavefront, for this linear source, the wavefront will be cylindrical in nature. Wavefront will be cylindrical in nature. So for a point source, the wavefront is spherical. Even for a spherical source, the wavefront is spherical. For a line source, the wavefront is cylindrical. So there will be multiple cylindrical surfaces. Now let's say we have a source which is neither point or line, but the light source is at very large distance, that is, it is at infinity. So the light rays which are coming from the light source are parallel. Okay, the light source which are coming are parallel to each other, light rays. So light rays are coming like this. So in this case, the wavefront will be in the shape of a planar surface, like this. So there are three different types of wavefronts that we can have. One is the spherical wavefront, one is the cylindrical wavefront, and one is the planar wavefront. So these are the three types of wavefronts that we have. So what is a wavefront? It is a locus of all the points which are in same phase. So according to Huygen, every light source emits some light in the form of wavefronts. Now after this, he suggested that these wavefronts, these individual wavefronts, they also act like a point source, and they also generate some waves which are called secondary wavelets. So he assumed that this individual points also acts like a secondary source. So he now introduced another term which is secondary wavelet. Secondary wavelet. So what is the meaning of this secondary wavelets? So let's say we have a point source. Now from this point source we have various wavefronts. let's try to draw. So let's say this is a point source from which the light is coming out in all the directions. We are only drawing in one direction so that it is easier to understand. Now what he suggested is that all these points on the wavefront acts like a secondary source, and they produce secondary wavelets which allow the light to travel in forward direction. So what he suggested is that this point acts as a secondary source. So this is called the secondary wavelet. So what he suggested is that this main source emits some wavefronts like this, okay, and all the points on this wavefronts again act like a secondary wavelet, and they create another wave. So this another wave is transmitted like this. So all these points will act like a secondary source and create another wave. So according to Huygen, first of all the source produces the wavefront, and the points on the wavefront produce secondary wavelets which allow the light to travel in the forward direction. Now he assumed a few things. So let's write them. So first of all, according to Huygen, let's write everything down. So every point on a given wavefront can be regarded as a fresh source of new disturbance or new source of light, and sends out wavelets called secondary wavelets. Now these secondary wavelets spread in all direction with the velocity of wave, that is velocity of light. But one thing that he assumed is that the secondary wavelets only travel in the forward direction, or you can say, or in the direction opposite to the, or in the direction away from the source. So what does it mean is that this wavefront only allows the light to flow in this direction. There will be no light in the backward direction like this. So this was the assumption of Huygen. So according to Huygen's wave theory, there is a source which produces wavefronts. All the points on wavefront produce secondary wavelets which allow the light to travel in the forward direction. So this is the Huygen's theory of wavefront. Now on the basis of this theory, Huygen was able to explain reflection, refraction, interference, diffraction, etc. So we will now move on to the Young's double slit experiment, which quite firmly established the wave theory of light given by Huygen. So now first let us try to understand the meaning of interference, and then we will move on to the Young's double slit experiment. So interference of light. So what is interference of light? So let's say we have multiple light waves, then it can happen is that all these light waves interfere with each other or interact with each other to produce some other resultant light wave. So what is interference? Interference is the redistribution of light energy due to the principle of superposition. We have understood the principle of superposition in the previous chapters. Due to the superposition of light waves coming from different sources. Now here one condition we will enforce is that those sources are two coherent sources, so that we can have sustained interference, that is the interference pattern is remain as it is, it does not change much. So for that we will assume that the sources are two and they are coherent sources. We will study about the meaning of coherent sources, and this phenomena is called interference of light. So whenever we have, let's say, two coherent light sources and they superimpose with each other by the principle of superposition, then this redistributed light energy is the resultant light, and this phenomena is called the interference of light. So interference is simple. Interference is the superposition of light waves. So there can be three types of or multiple types of interference, but we will be discussing about ideal cases, two ideal cases. So one is called the constructive interference and one is called the destructive interference. Constructive and destructive. There can be the cases in which there is no complete constructive or no complete destructive interference, but we are not going to go into that. So constructive and destructive interference. So let's say we have light sources like this. So let's say the input light sources are like this. I am trying to draw it exactly as it is. So let's assume they are completely overlapping. So in this case the resultant will, this is input 1, this is input 2, and this is our resultant. So the resultant will have the higher amplitude which will get added up. Okay, this 2 will get added up, this 2 will get added up. So because of that we will get a light wave with higher higher amplitude. So this is the constructive interference. Now what happens in the destructive interference? So in destructive interference we will have a situation in which the light waves are in opposite phase. Here the phase is same. Okay, so let's say one light ray is like this, so the other light ray will be like this. So here what we will have is that we will have no amplitude whatsoever if these amplitudes are equal. Okay, so we will have no amplitude remain. So this is the destructive interference. Again, this is the ideal condition. We can have a situation in which we can have no complete constructive or no complete destructive interference. So these are the two types of interference that you will observe. Now in this constructive and destructive interference, let's write a few formulas which we will use in the Young's double slit experiment. So when we have a situation in which we have constructive interference, so in that case the intensity of light is given by, in this case the intensity is maximum. Okay, intensity of light is maximum, and in this case the intensity of light is minimum. Intensity is minimum. So when we have constructive interference, the resultant intensity will be equal to I1 plus I2 plus 2 root I1 I2, which is greater than the individual intensities. It can be said that maximum intensity is proportional to amplitude 1 plus amplitude of the second wave whole square, because remember intensity is proportional to amplitude square. Remember this thing. And in the case of destructive interference, the intensity is given by this formula. So here the intensity is less than the sum of I1 I2, or in this case intensity is minimum, which is proportional to A1 minus A2 whole square. So this is the case of constructive and destructive interferences. And now we will discuss about the meaning of coherent source, and then we'll start the Young's double slit experiment. So what is the meaning of a coherent source? Coherent source of light. So let me write the points. First point, a coherent source of light is a source continuously having same frequency and wavelength. So coherent sources, remember when we have multiple sources, so when do we call them coherent? When the light waves are of same frequency or wavelength. And second point, both these points are necessary, and the phase difference between the waves is either 0 or constant. That is, let's say if the phase difference is 90 degree, then it remains 90 degree. If the phase difference is, let's say, 170 degree, it remains 170 degree. If it is 130 degree, it remains 130 degree. So the phase difference between the waves must be constant, and the light waves must have same frequency and wavelength. So if they satisfy these two conditions, then we say that the light sources are coherent light sources. So why do we need coherent light sources? So what are the conditions? What are the conditions for sustained interference? Sustained interference is the interference in which the interference looks the same throughout the time period. So it does not change over the time period. So what are the conditions for that? So first of all, two sources of light, the two sources of light must be coherent. Otherwise, if the phase difference is changing, then the interference pattern will keep on changing. Okay, so the two sources of light must be coherent. Amplitude of the waves from the two sources must be equal so that we can have proper destructive interference or minima that we can obtain. Otherwise, if the amplitudes are not equal, then we will not obtain zero minima or complete destructive interference. Apart from that, the sources must be very small, very narrow, or point source. Why? Because a wider source will act like multiple sources in itself, okay, and we do not want that. Next, the separation between two sources should be as small as possible. Why? Because if the separation is large, then there will be a part difference and there will be some change in the location. So we want this sources to be as close as possible. Apart from that, the sources must be monochromatic. Now what is the meaning of monochromatic? It means that the wavelength must be only one, that is only one light should be there. For example, let's say red color light or blue color light must be there, and that too having same wavelength, because red color also has some range of wavelengths. Also the interfering waves from the two current sources of light should travel in the same direction. So waves must be traveling in the same direction. So these are the conditions for the sustained interference, so that we can have a proper destructive and constructive interference. So now from the next part we will start the Young's double slit experiment.